dark.
Going dark. I'm going ghost.
Don't fall asleep. It's tempting.
Looks expensive.
Expensive and tempting.
I'll be back.
We'll be here. All right, so thank you for sticking around for this. If you don't know me, my name is Nick Macias. I teach engineering computer science here at Clark. And I wanted to give a short, probably about 25, 30 minutes, talk on these things called FPGAs, Field Programmable Gate Arrays. And the reason for talking about this are a few things. One, it's one of my favorite topics. They're fun toys to play with. They're devices that we're starting to introduce into the Engineering 250 class. So how many people here have already taken Engineering 250? Okay, so if you've already taken it, we've talked about some of the things that lead up to this. If you haven't taken it yet, you'll probably get a chance to actually play with some of these devices when you take the course. So I said I was going to talk about FPGAs, and I was going to talk about some of the history of it. And with history, there's always a question, where does the history begin? Because nothing really just springs out of nothingness, right? So how far back do you go? So I decided to start this history way back with these. So what are these things here? They're vacuum tubes, right? We don't see them very often anymore. Vacuum tubes were the way that electronics was done not too long ago, okay? 60, 70 years ago, everything had vacuum tubes in it. TV sets, radios, and these are physically big devices, okay? And they do basically two things. They do power amplification, but they can also work as an electrically controlled switch. So you can use it like a light switch that you flip a piece of plastic or push a button. But these switches, you can control whether they're on or off with electricity, which means you can put these together and have one of these controlling another one of these. And as soon as you can do that, you can start to do things like say, is this switch on and is this switch on? Or you might say, is this switch on or this switch? And you can do logical operations. So in the mid-1800s, people realized if you can do these logical operations, what we call Boolean operations, you can do things like code algorithms. And about 100 years later, we started building machines that took advantage of this. So this is the ENIAC computer. It's an early programmable system. It was built based on vacuum tubes. And these people are actually inside the computer, right? The computer is this whole room. And it was huge, just humongous form factor. And it's got all these wires and all kinds of stuff behind the wall that you can't see. Frightfully expensive and huge and power-hungry system. So what is this thing? This blob-like looking thing? Who wants to venture a guess?
Transistor LED.
Transistor LED. Other guesses? Capacitor. Blob of jelly that does what a muscle does if Scotty were here. So this is a transistor. This is the very first transistor. Okay, it was developed by John Bardeen and Walter Brattain at Bell Labs 1948. William Shockley was their boss. And this was not a very high priority project at Bell Labs. It was kind of a skunk works sort of project. And it was almost canceled the year before by William Shockley because they were just having terrible luck trying to get any results out of this. But they kept pushing through, and in 1948, they were able to achieve power amplification with this. Now, all three of them won a Nobel Prize for this work, which is pretty cool. But for various reasons, William Shockley was not listed on the patents. So he was upset by that. And his response was to begin his own sort of secret research to try to come up with a better transistor that would be his. And he was successful in this. He came up with a lot of different devices, really advanced the field, and then he left Bell Labs to start his own company, Shockley Semiconductor. It turned out he decided he wanted to move closer to his mother, whose health was failing, and she lived in Palo Alto, California. So that's where he moved, and that's where Shockley Semiconductor started. And that's one of the reasons Silicon Valley is in Palo Alto area. So he hired a bunch of PhDs from area schools and schools across the country and developed a really top-notch team, brilliant physicists, and they started trying to improve technology related to transistors. Apparently, William Shockley's personality was difficult for some people to get along with. There were lots of conflicts, and at one point, Shockley canceled the project. And 8 of his top engineers decided they had enough, and they left altogether. They were dubbed the Traitorous 8. You can read all kinds of articles about them. The Traitorous 8 left Shockley Semiconductor and started a company called Fairchild. And from Fairchild, you can draw a direct line to about 60-some spin-offs. One of the Traitorous 8 was a fellow named Gordon Moore. Anybody know what spin-off he started? Intel Corporation, you may have heard of them, right? So it's a very direct line from this odd-looking device to basically Silicon Valley, and basically the world as we know it today from a technology viewpoint, right? And it all kind of came from this thing, this transistor. And so we can design circuits using transistors. So each of these little funny-looking symbols, that's a transistor. And the squiggly lines are resistors. If you've taken Engineering 120, you know what a resistor is. These are LEDs, so for output devices. And this is a 2-bit adder. So it lets you put in 2 numbers, each number between 0 and 3, and it produces a coded representation of the sum on these 3 lights. So if you've done 250, you've built a 2-bit adder, and your circuit was probably simpler than this, right? Because designing with transistors is fairly cumbersome. And the physical layout of these things gets kind of big, so each of these little circles up here, that's a transistor, and it's about, you know, a quarter of an inch across. This is a 1-bit adder. So you take 2 of these and put them together, and you get a 2-bit adder, and it's kind of a big board, but certainly smaller than if you use vacuum tubes. So what is this thing?
That looks like a microscope image, right?
It's actually about an inch across, I believe.
That's a little big.
So it's pretty big.
Integrated circuit.
Integrated circuit. This is an integrated circuit. So what does integrated mean? It means it has multiple things on it. And this thing had 2 transistors on it. Okay, that big blob we saw in 47, that was a single transistor. This had 2 transistors on it. And it was invented by someone named Jack Kilby, working at Texas Instruments, and he also won a Nobel Prize for this work. But more importantly, if you've taken Engineering 250 and you dealt with JK flip-flops and you've cursed them, you were cursing his name, because JK flip-flops were named for Jack Kilby. So that's an even greater honor than a Nobel Prize, probably. So 10 years later, integrated circuits looked like this. So this was about 1 millimeter on a side, tiny, had 5 transistors inside, and this worked as an amplifier. So in 10 years, we went from this to this. And now we were on a roll, right? This was mass produced and was used for portable amplification. And so we can design circuits from this. So here's a 2-bit adder designed with these integrated circuits. And each one of these things is a modern version of that blue thing with blobs all over it, right? It has a bunch of transistors inside, 10 or 15 transistors each. And we put it together on a board with some wires. And that's pretty cool. That's a whole lot better than what we were doing with vacuum tubes. But this can get really large pretty quickly too. So here's an implementation of a clock. Right, hours, minutes, seconds, using integrated circuits, and it's, you know, about that big. This is 1970s technology. I had a digital watch when I was in the 70s, and it showed hours, minutes, seconds, and that was it. So they had to shrink this down to where it would fit on your wrist, right, without making you look really kind of geeky. So what do? We have these integrated circuits that are nice to work with, but we still end up with big form factors when we put these things together. So the trend has been to put more and more things inside one of these chips. So this is 1976 vintage Intel processor. This is the 8086. This was basically from where all of the current x86 architectures come from. Okay, they're all backwards compatible to this version. And this had almost 30,000 transistors on it. And it's a big chip. It's bigger than the ones we work with, but it's still small enough you could fit it inside a circuit board and have plenty of space for support circuitry around it. So this was about 29,000 transistors. And this was a real breakthrough, this idea of application-specific integrated circuits. Instead of taking these predefined chips, you design your own chip for what it is you want to do. We want a computer, design your chip for it, have somebody manufacture it. And they actually create a custom chip based on your specification. And this is great. These things are reliable. They're relatively cheap to buy. A few bucks gets you one of these chips. They don't take a lot of power because everything's happening inside this chip. You're not driving these big wires from chip to chip. And they're easy to work with. You could actually take this chip and pop it into one of those proto boards and wire things up to it. And they keep getting bigger every year. So how many people have heard of Moore's Law? So this is Moore as in Gordon Moore, right? And it's really an observation that roughly every 2 years the size of these chips doubles. So way back here in the early 70s, the first microprocessors, a few thousand chips. 30 years later, year 2000, around 10 million transistors per chip. And 2010, we hit the billion transistor mark. And so this is an exponential, right? This is linear time. This is exponential number of transistors. And this seems to keep going, and people keep predicting the end of Moore's Law, and we just keep pushing right through it, keep finding new ways to do things that get past these impossible roadblocks. This is the end. The world's going to come to an end, right? And this law has just persisted for decades. So this looks great, right? Well, guess what? There's a dark side. The dark side is Moore's second law. So Moore's second law says the cost of the manufacturing plants also doubles roughly every 4 years. So the facilities where you build these chips are getting more and more expensive. And right now, a new foundry, $15–20 billion. That's the upfront cost to build a factory to manufacture chips. Really expensive. So how do they pay for this? They pass the cost on to you. So if you want to manufacture your own chip, you can expect to spend a few $1 billion for the first chip. Now once you have that prototype, if you want to start turning the crank and spitting out a bunch of chips, relatively inexpensive. But that first chip, $3 million nominally. And that's a ridiculous amount of money. Right? So imagine you're in your circuits class, and you've written your schematic for your circuit, your airplane landing controller, and you're ready to test it out. You want to actually build it. So you go to Izad and you say, okay, I'm ready to build my chip. And he says, okay, give me $3 million. And you pay him $3 million and he gives you your proto board and you get one chance to wire it up. And you wire it up and you test it and it's like, oh, I wanted that to go to pin 6, not pin 7. Okay, give me another $3 million, you can try again. And this actually caused problems for a while in the industry because nobody would do the final sign-off on their designs. Because if you were the signature that said, this design is perfect, and it didn't work, and your company was out $3 million, that might be your job. So there was a real problem with sort of this brain lock of like, how do we reconcile with the cost of this? And that cost keeps going up. So here comes FPGAs. So FPGAs were seen as a solution to this problem of increasing these one-time costs of chips. So a field programmable gate array, here's the basic idea. It's a chip, okay, that was already manufactured. It's not custom manufactured for you. You buy it, and it's already been spec'd out. Has a fixed physical design, but you can customize it after you buy it. You can load information into it that basically turns it into a different kind of circuit. So it's kind of like a soft programmable piece of hardware. And it's a mix in between sort of a programmable computer and a fixed piece of hardware. Computers are great because you can write the code, you got a compile error, change it, rerun it, takes about 15 seconds, right? Hardware is very difficult. It's going to take you months probably to change your design, get another chip manufactured, plus all the money. So post-manufacturer customization. Today's FPGAs are completely reusable. Okay, we're not physically changing the structure when we program them. It's more like a flash memory. So you can reprogram them again, and again, and they're non-volatile. You program it, you disconnect the power, you plug it back in next week, it's still programmed. So these are very, very useful to deal with. And it was really Cisco that kind of like springboarded FPGAs into the popular go-to device. When Cisco was coming up to speed in the 90s, they were building routers, right? Connecting networks together. This was where the internet came from, basically. And they needed a lot of really fast processing. They wanted to do it in hardware. They didn't want to pay the upfront cost. This was a two-person team in a San Francisco flat, right, doing this work. They went for FPGAs, and they became one of the biggest consumers of FPGAs through the 90s and early thousands. So here's the first FPGA, the Altera device up here. And it's got this little window here. You can look in and see the circuitry. This was what we call UV erasable. You could program it electrically, and if you made a mistake and you wanted to reprogram it, you took this and you put it in something like a tanning bed, basically, for chips. It exposed it to ultraviolet light for about 20, 30 minutes, and it would erase the program, and then you could reprogram it. And that was fantastic, right, compared to sending something out to a factory. So that was made by a company called Altera. Altera is still around in the FPGA business. The following year, Xilinx introduced their first chip. This had 64 programmable devices inside. Xilinx is the biggest player in FPGAs today. Just for the sake of the timeline, my favorite example, 1986, the following year, Cell Matrix introduced their first programmable device. And this had a humble 12 programmable devices inside, but it was designed so that each of these could actually program other elements inside itself. So the Cell Matrix chip was designed to make circuits that could introspect, self-analyze, self-modify, self-repair, self-replicate, and in some way, shape, or form possibly start approaching on something kind of like self-consciousness or self-awareness. That was sort of the dream down the road. Never took off, but that's a whole nother talk. So today, Xilinx dominant share of the market, about half the market space. So these are millions, so total market space, $4 billion, about half of it Xilinx, almost half of it Altera, which was bought by Intel recently, and the others are kind of much smaller, but still available. Microsemi in particular is still around. So this is a big field. And the basic concept inside, this varies from one processor to another, but basically we have a whole collection of these little programmable devices. And the specifics of that device, that's the secret sauce of each vendor. But it's something that has, some logic blocks and some flip-flops and some multiplexers and a way to say, okay, I want you to take two inputs and tell me if they're both 1 and put out a logic 1 if they are. Or I want you to take 3 inputs and add them together as bits and give me the sum and the carry out. So you have these programmable devices, and then scattered throughout these, you have these little interconnection matrices. So you can say, okay, take the output of this and connect it to the input of this. And so you can build your circuitry basically, but you do it all through software. And then there's I/O blocks for actually taking the signals in here and sending them to and from the outside world. And that's the essential idea of all of these devices. So the question is, how do you specify what this circuit is going to do? How do we give the chip this information saying what each of these blocks should do, how we should connect things together? So we need some kind of language, something like a programming language. It's called a hardware definition language, an HDL. And the two main HDLs are Verilog and VHDL. VHDL was designed by committee. It's a older standard. Verilog generally seems to be the one that's more popular, and it's the one that we mostly teach in 250 here. But same idea for either of them. They basically let you write lines of text in a file that describe the circuit you're after. So you take that file with your circuit description, you run it through something like a compiler for a regular software program, but it compiles it into an internal form, which you can then run into another piece of software to test your circuit. So you can stimulate the inputs, you can look at the outputs, you can decide whether or not it's working correctly. You can analyze the timing, how long does it take to change an output when you change an input, and so on. And then when that's all good, you can run it through still more software and get a configuration bit stream. A bunch of 1s and 0s that if you load into your device, will actually program it and cause it to do whatever it is you want to do. So let me pass some of these around while we're at this point. So these are some examples of FPGAs. And the big chip in the middle is the actual programmable device, and everything else is just sort of there to make space for it. And those boards are really just bare FPGAs. But we've also got the option of bigger boards that have buttons and lights and connection points and all sorts of things like that. So let me start these in the back. Pass them around. Yeah. And these are fun to play with. All right, so that's the basic, what we call the tool flow. That's how you go from your original description of your circuit to eventually configuring your circuit so that it will actually implement your circuit. And with Verilog or other languages, there's really two fundamentally different approaches to this. Okay, the first approach is what we call a structural approach. We can take a circuit, so here's a 2-bit adder again, right? 2 inputs, input A and B, and 3 output bits. And we can do the usual hard engineering that we do in classes, where we figure out what this circuit should look like. We want this kind of gate here, and we want this output to go into this input, and so on. And we can write a file that describes this circuit. So that's a structural approach. We develop a schematic for our circuit, and then we write a file that says what we want. And instead of putting those chips on a physical board and connecting wires together, we make a line of text in our file that says, we want this kind of gate, or we want the output of this gate connected to the input of that gate. And that works great, but as your circuits get more and more complex, so do your files. So here's a 4-bit adder. It's got 2 4-bit numbers, A and B, so this can add numbers from 0 through 15, and a 5-bit output. And there's a lot of gates in here. So in our Verilog file, we have to describe each of these gates, and we have to say, okay, I want this input on this gate to come from the output of this gate over here. And it's almost as error-prone as actually building it up with wires on a proto board. Right? This would be a nightmare to code. The only difference is you're typing lines of code and editing and checking instead of staring at wires on a physical board. Not an ideal approach. There's a totally different second approach, and this is the real power of Verilog. This is to use a behavioral definition. With a behavioral definition, we don't say how the circuit should be built, we say what the circuit should do. Okay? This is how the circuit should be built. Here's a gate, connect them to this gate, and so on. Behavioral definition is much simpler. We want an input A with 4 bits, an input B with 4 bits. We want a sum with 5 bits, and we want the sum to be equal to A plus B. And that's all you need. And the software tools, the Verilog compiler, will take this and effectively translate it into this. So when you can build something with this complexity by just saying assign sum equals A plus B, now you're in a totally different paradigm. Right? We can do some really powerful synthesis of electronic circuits using this kind of approach. So behavioral Verilog is the real key. And once you can do this with 1 line of code, well, the things you can do with 100 lines of code, you can just imagine. Right? You can design an entire microprocessor with a few hundred lines of Verilog. All right, so it's demo time. And for this demo, I want to pick on the example we've been picking on, a 2-bit adder. But instead of having 3 lights for the output, we want to actually use the output as a little 7-segment display, something that displays a number that looks like a number we're used to. So again, if you've done 250, you've done this in a lab. I had a student just finish this. I asked if I could take a picture for this lecture. He said, sure. So this was the student's circuit board for the 2-bit adder. And your 2 bits come in here, and there's all this circuitry with several chips doing the calculations, and then here's the 2-bit adder. It looks like it's displaying a 2 right now. Okay, so that's the approach if you're building this thing out of individual chips. So what I want to do in the last few minutes here is look at how we could do this using some Xilinx software. And so one of those boards that's going around, the small one, that's actually a Xilinx-based FPGA board called a MEMIS FPGA. That's the one we're using in 250 this quarter. So I want to look at some software for doing this, and we'll see how far we get. So the software for this is always custom to the vendor. Every vendor has their own version of the software. And it's big, and it's complicated, and it breaks a lot. So it's good fun to use. And I'm just going to start a new project. So I'll call it ECS Club Adder. And there's all this information you can set up in here, but basically on that physical board, that big chip in the middle, somewhere on there in faint ink it says XC6SLX9. That's the type of FPGA. And the package, TQG144, Q means it's a quad pack. It's got pins on all 4 sides, and it's got 144 pins. And I knew this ahead of time, so I already set this up for us. But this software will work with a lot of different types of devices. Okay, so I've got a setup for a new type of FPGA project. So I'm going to put in some files. So I'm going to say, let's add a Verilog module. And I'm going to call it adder. And it writes comments for you, right? That's always nice. So I've got a big block of comments here in the beginning with the project name, and the engineer's name is missing and so on. But I'm going to get rid of all of this because I actually have the code already written ahead of time, so you don't have to watch me type. So there's the Verilog code I'm going to put in. And so the top block is comments. This is basically just saying I want 2 inputs A, B, and I want to drive this 7-segment display. Okay, there's some of them on that bigger board that's going around. So I've got to control 7 individual lights that will turn on and off in different orders. For example, if I want to display the number 3, I would turn on those 5 LEDs, and I would leave these 2 off. And that'll look like the number 3. So I've actually got 7 outputs for those 7 segments in the display, and I've got 2 inputs, 2 bits each. And I've got an answer, which I call num, which is 3 bits, and there's the actual code. Num equals A plus B. And in 250, we have another chip, it's called a 7447, that would take these 3 bits and use it to drive these 7 segments. Well, I didn't have room on the circuit board I used for a 7447, so I made one ourselves. So basically, if your number is 0 or 2 or 3 or 5 or 7 or 8 or 9, then I want to turn on the segment A. And if it's 0, 1, 2, 3, 4, 7, 8, or 9, I want to turn on segment B. And sat down on a piece of paper with these 7 segments, just figure out which things to turn on for each digit you want to display. And so these 7 lines of code will translate that 3-bit number into this nice 7-segment output. So that's half our code is this right here, and it's really 1 line of code for doing the addition and then 7 lines for driving the display. And the only other thing you have to do is we want to actually physically connect this board to a circuit. So yeah, that's nice and visible. So here's the FPGA board. That's the actual FPGA there in the middle. This is the cable. It's just a USB cable. I'm going to use it to program it, and then we're going to use it for power. And these holes along the edge here, we can use as input and output lines. So when I said output G, one of these holes along the side is mapped to that output. And my circuit board over here basically has my switches on it and my 7-segment display and 1 resistor. So we've got to tell the FPGA which pins on this device, which pins along here we want to use for those inputs and outputs. So that's something called a configuration file. So I'm going to say add a new source, and it's going to be a constraints file, and I'll just call this pins. And again, I've already written one of these. So I'll just paste that in. And this is really just saying this thing that I call G should go on location P6. And the thing that I call F should go on location P7. And when you're actually working with this, none of it is spelled out for you. So you've got to do things like go in and look at the schematic. And you got to be able to read this stuff. And the higher up you go in engineering, the more advanced things you're working with, the more you have to do yourself. Right? So you've got to know what all this stuff means, and you've got to understand that, oh, okay, I want to get to this particular output, so where does that go? It goes to this thing that's got this label on it, and that's something that's mapped back here on this page of the schematic, right? So you end up doing a lot of engineering along the way of trying to read these things, and that's just because the level of complexity. All right, so there's my constraints file. This maps my signals, A and B, and my outputs to particular locations. And all of this stuff is mostly just given for you. And you copy and paste. So let's go ahead and compile it. And there's this big green play button over here. You click that, and it starts compiling after you save it. So it's running through a series of steps. This one is called synthesis. This is called translate. And on something this size, this will take about a minute. When I was in grad school doing this, I had some designs I would run, and it would take about 70 hours to finish compiling. And it would usually finish by saying internal error, contact vendor. And it meant that you had found a bug in the code, and you contact the vendor, but nothing ever happens, right? So this is kind of the pinch point for large designs sometimes, is the software tools, right? It always comes down to software. This is a smaller design, so everything came through okay. It said generate, post, place, and route static, timing completed successfully. That's our last step. It says no processes running. Everything is good to go. So we've compiled this design now, and all I got to do is figure out where the steps are. Here we go. All right, so it did synthesize. There's a little exclamation mark there. There's some warnings. I'm ignoring warnings. Implemented the design. That's fine. So at this point, we could go ahead and do some simulation. Okay, and there's a whole nother set of tools we can use to simulate. We're not going to worry about that. We're just going to go straight to the hardware. So I'm going to go down to where it says generate programming file. And out of the millions of options, there's one that we have to change, which is create a binary configuration file. And now I'm going to say generate. And we'll see where this gets us. And this is usually pretty quick. So that's successfully completed. All right, so I'm going to take my board and plug it into a USB port. And I'm going to run some software that will let me take that bit stream and load it into this device. So I'm going to browse to it. I forget what I called it, ECS Club. So files, Xilinx Webpack, ECS Club adder. And there's my adder.bin. And I'm going to say program board. And while it's programming, well, we don't get to see a whole lot, but when I started, some of the LEDs were blinking and so on. But it's basically loading these bit streams, this bit stream into the FPGA and a fairly accurate progress bar. And when it's done, it'll read it back from the device and compare to what it wrote and make sure that everything got written correctly. And then after that, we should have a good device ready to go. So the verify is usually quicker than the programming. says flash verification successful, programming done. And I knew this was going to happen. So I tried this yesterday, and it failed on me. And it's failing today. But we'll give it one more shot.
I think that's one of the big differences between enterprise software
Yes.
and consumer software.
Are you in
Enterprise
the
software is not fully tested.
correct group to access the device?
Well, I had it set so it didn't matter, but it apparently matters now. Yeah, so this is running under Linux, and as often happens, the Linux version of things is done by the community, whereas that earlier software we saw was done by Xilinx. And it's a free package, but it's still commercial. Whereas the programmer we're working with right now is a freebie that was just developed by people trying to make this work. So it can be a bit of a moving target. But let's see how it does here. But while it's doing that, let me show you something else here. So remember, we had basically one line of code here for the sum and then 7 lines to do the assignment. So we can go under Tools and we can say Schematic Viewer, and we can say let's do an RTL view, Register Transfer Language, view of this design, and it will show us what it came up with. It came up with a block called an adder. So this is called a system diagram, inputs and outputs. But we can click on it and it will show us what's going on inside. So there's some OR gates, and there's an adder module, and there's some big OR gates and some inverters, and this is basically the solution it came up with to implement that Verilog circuit. Now we can also say, schematic viewer, let's look at it based on this particular technology. Let's look at the schematic for this FPGA. And so top level view, it looks like this, but when we go inside, we see these combinational blocks. These are those CLBs inside the Xilinx device. And they're configured to do different functions. So if we click on one of these, we can see a circuit diagram for what's going on in this particular block. And if we want, we can click on equation. It'll show us the Boolean equations. You should be getting 250 flashbacks right about now. So that's the equation that I was configuring into the schematic. To do that, it turned it into a truth table, and guess what? It also makes a K-map. So it's doing all these things that you do in your 250 labs in order to come up with this implementation. All right, so I cannot get this thing to configure. This is a work in progress. And unfortunately, the grand demo of all of this, which was my beautiful 2-bit adder, is not going to work today. So I'm going to have to leave you waiting to see that another time. Let me try one other thing, though. Let me just try loading in a different file in case I forgot to do something. So I'll try this one last time. And working with FPGAs is a bit of an art form in addition to an engineering practice. And you can do everything by the book and still get a design that just doesn't work very well. And the reason that if you go on websites and you look at job positions and you see $150,000 for an entry-level position in FPGA design is because the more experience you have with this stuff, the better you are at working with it. Okay, and it's not at the point where you can just plug in your code, hit the button, and you're done. There's a lot of finagling you have to do. There's a lot of understanding the details of how this device works the timing characteristics and issues and so on and so forth. So it's a fun way to do engineering. So, and with that little pause, so now we have our 2-bit adder working correctly. So that's 0 plus 0, and I can toggle in a 1, there's 0 plus 1, and we can toggle this, there's 1 plus 1 is 2. I guess we should be doing it like that. So there's a 2, and we can do 2 plus 2, and that's 4. And we can do 2 plus 3 is 5, and 3 plus 3 is 6. And the only thing on this circuit board that I had to wire was just the switch, the LED, and one resistor, and everything else is just connected to the FPGA board. And this is where all the circuitry is, right? The 2-bit adder, the 7447 decoder, and everything else. It's inside here. And you can take this and plug it into your backpack power source, and you've got your FPGA. You can take it on the road with you. All right, so that's all I wanted to talk about. So thank you for that. And if you got any questions, happy to take questions. Otherwise, thanks for your attention and enjoy your long weekend.